Okay, gang, just going to get started here with chapter 27.3, our star groups. Exciting, one of my favorite, Our objectives out of this is we're going to describe the characteristics that identify constellations. We're going to describe the three main types of galaxies. We're going to explain the Big Bang Theory. Pretty easy, pretty straightforward, but really exciting because I love looking at the stars. So, the first thing that we're going to talk about is that constellations. Constellations are basically groups of stars, and these stars we only have about 88 that we identify currently. That we know as an accepted constellation, but constellations have been around for since the dawn of time, since man has been here. And what it is at night, back in 3,000 plus years ago, what did people have to do? It wasn't like they could go watch the Tonight Show, or they could go watch the evening news, right? So they would look up, and so what they would do is basically connect the dots of the stars, and they'd come up with imaginary animals or gods or goddesses and heroes, and come up with some way to connect with the sky. And so what we see is the constellations, what they are, groups of stars. Basically, it was a way for people to connect with them. And so a constellation is something like one that you're pretty familiar with, Orion the Hunter, right? And so civilizations have had stories about Orion forever. In fact, what we now know is that Orion, the belt of Orion, actually is laid out and was so revered by Egyptians that the pyramids are laid out in the shape of Orion. And so these constellations, right? So they were a way to connect with the gods, or to connect with the stars. An asterism is like a part of a constellation that makes an image as well. And so one of the best asterisms out there is the Big Dipper. The Big Dipper is actually a portion of Ursa Major. Ursa Major is the bear, right? The big bear. And so a small portion of it is the Big Dipper. The Little Dipper's up there as well. So constellations, one of the things that you might be pretty aware of is, what's your zodiac sign? Well, I happen to be a Gemini. So I was born on June 7th in 1970, and I'm a Gemini. And so, my question is what's your sign? Most all of you know what your sign is. Now, don't confuse astronomy with astrology, right? So astrology is some sort of a motivational statement, or like what your future holds or whatever, just by reading your sign that particular month. And so we have the zodiac. Now, the zodiac, all of the symbols of the zodiac are on what we call the ecliptic. And the ecliptic is the direction which the sky rotates due to our pole, right? So our poles, our axis of our Earth is spinning on its axis, and as it is, that ecliptic is the constellations that are at eye level on that. And so we have all the zodiacs on there, whether it's a Libra or a Cancer or Pisces or a Gemini. They're all on this zodiac, are all on this ecliptic. And so that's where those constellations lie. A galaxy. Well, if you look up in the evening and looking from the southwest to the northeast at night, you'll see a white light. It's dull, and if you're out in the really black areas, it gets pretty bright. I was out on the ship in the Pisces in in the ocean with Noah, and there was no lights out there whatsoever. Stars I've never seen so bright in my life, right? So when we have a bunch of stars clumped together, we call them a galaxy. And if you think about it, galaxies have billions and billions of stars in them, and so it could be as much as I don't know, 100 billion, 200 billion stars in a galaxy, depending on how big it is. And it could be not very big too, right? So what's interesting is if we look at our Milky Way is a type of galaxy, which we're going to talk about. Now, our local group contains 17 galaxies within our area. So there's galaxies that are basically clumped together. On average, about 100,000 light years across. On average, about 1 billion stars per galaxy. And what are stars, right? So a star is a bunch of gas, dust that's come together, and we've already gone through the stages. Well, it makes sense that we have stars, gas, dust, nebula, another word for gas, black holes, right? And planets, and all these other things, asteroids, comets, etc. So we have all this material out there that's making up our galaxy. So our main types of galaxies, our first one would be a spiral galaxy, and it's exactly the way it sounds. It has arms and it's spiraling out of the center. And so to kind of take a look at a spiral galaxy, here's a spiral galaxy, and we have a massive center, and then you have these arms coming out of it, and these arms are the arms of the galaxy. That is a spiral galaxy. And so again, you could have black holes in this. And as we talked earlier, how do they find black holes? They look for where stars are or should be, and they see nothing, probably a good indication that we have a black hole there. Barred spiral, exactly the same as a spiral, except there's a bar through the nucleus, right? And so, it's, I'll show you a picture. This is by the way, that's a galaxy on its edge. I thought that was pretty cool. These are two galaxies that are spinning together. Look at this. And so as it's spinning, eventually these two galaxies will be one galaxy. Here's a barred spiral. We have this bar going right through the nucleus of the galaxy, and as it's spinning out, you've got your arms here. Well, if you look really close, you've got other galaxies that are behind this galaxy, and you can see them. This is a great image by the Hubble telescope. Okay. Oh, this might be almost a barred spiral, right? So it's got a bigger elongated nucleus. Look at, there's many arms in this spiral. You don't know where it starts and stops. But one of the things that you note is that all spiral and barred spirals have a lot amount of gas. And I'm not just talking like 3-bean burrito night after Taco Bell type of gas. We're talking massive amounts of gas. And so this gas is giving rise to new stars, and so these are the star makers, right? These types of galaxies. So we have a pretty even mix of new and old stars in both of these types of galaxies. Okay, so I just love this picture. I really do. The two galaxies coming and spinning together. Then we have what we refer to as an elliptical galaxy. Again, elliptical. What is the shape? It's an ellipse. And it's no arms or no real nucleus that have arms coming out of it. It does have a nucleus where the middle of it is. But these are kind of older. And what we refer to these as, there's not a lot of gas. There's not a lot of dust. They're not giving a lot of birth to new stars. So we tend to think of these as older types of galaxies. And then you've got the galaxies that have really no shape whatsoever. And so these we refer to as irregular galaxies. And they're just a bunch of stars, and they're just hanging out there. Interesting to think about, our Milky Way galaxy actually has two irregular galaxies very close to us. So if you're in the southern hemisphere and have a good telescope, you can see these. This would be just a irregular galaxy. There's no pattern to it, There's just a large Magellanic cloud sitting here. But yeah, there's no real pattern to the cluster, right? So if we think about our Milky Way, our sun, the sun, is one of about 200 billion stars in our Milky Way. And to think about that just puts things into perspective. I mean, but what's cool is our sun is just right. We refer to that as like a Goldilocks sun, a Goldilocks star. Just right. Not too big, not too small, not too hot, not too cold. Just right for where we're at. And so our sun traveling is about 220 kilometers per second. And it only takes about 240 million years to go around the entire Milky Way. Because again, we're spinning. So to date, we think that approximately 20 trips have been taken by our sun to go around the Milky Way because it's only so old. And so only about 20 trips. That's incredible, right? So the center to sun, we have about, of the galaxy, about 30,000 light years. So it would take 30,000 light years for you to get from our sun to the center of the galaxy. The thickness of our arms, because it is a spiral galaxy, and we know that by using our telescopes and being able to figure out positions of stars, but the thickness is about 2,000 to 3,000 light years somewhere from across the arm. And then the edge to edge, so side to side of the galaxy, is about 100,000 light years across, give or take a couple thousand light years, of course. So that's our Milky Way. We also have what we refer to as open star clusters or open clusters, right? And basically, it's just a bunch of stars hanging out, and we're able to see and count the individual number of stars, right? They're just sitting there. And so that would be a star cluster, right? So here is a irregular galaxy, just star clusters within this galaxy. Again, clusters of stars. A globular cluster. If we have a globular cluster of stars, basically the stars are spherical in shape in their form. You can have thousands to millions of stars in a cluster, and they're very difficult to count because it's hard to pick out the number. Binary stars, I think, are really cool because basically what they are, stars that are revolving around each other, and you can get multiples. You can get a double, you can get a binary star, you can get a double binary star, which is 4 stars revolving around, or you can get double doubles. You can get many. Here's a globular cluster of stars. Can't really count the number of stars in there, so you don't really know how many are there. We talked about this in our first chapter, the Big Bang Theory and the formation of the universe. Right now, the current school of thought is we're about 15 billion years old as all matter and energy in the universe. That's about as good as we can get. I think right now they're able to use a telescope and see back to about 13 billion or 14 billion years ago. And so this is when all of the matter inflated. It all spread out very quickly. And so the energy moved out, and then gravity took over, and so pretty soon we had galaxies and stars and planets. And, right now, obviously, it goes back and forth, right? So stars are born and stars die, and we've talked about that, and planets and all that. And so we're constantly evolving and changing. So quasars are kind of interesting. We don't actually know what quasars are. We have an idea, but about 1960, they found these things that were giving off X-rays and radio waves. Again, using X-rays, you can see like even black holes, And so X-rays and radio waves were given off, and they didn't really know what they were. And they about 12 billion years old or so they thought. But what they think is they're about the first things to ever form in the universe. And so it's a theory. Not sure what quasars are, but that's what we think. I love this deep field image from the Hubble Space Telescope, and why I like it is these aren't stars. These are all galaxies. And what they did is they went to a portion of the nighttime sky that was particularly black, and they're like, hey, let's play around and see what this thing can do and see if anything's out there. And sure enough, on January 15th, 1996, which this is a very famous photograph, the Hubble Space Telescope caught the deep field, and in there, thousands upon thousands and thousands of galaxies. Pretty cool. So I want to show you also real quick the a double-double or a binary star going around itself, because I think it's something that everybody should see. So basically what happens is the two stars, as they go around each other, they basically are spinning in such a way that they're causing each other to spin around. And so here is, oh, that's not it. All right, I think this will have it in here.
Well, way out there in space, there's huge clouds of dust and gas, and if one of those clouds of dust and gas is massive enough, its own gravity causes it to start to collapse, so it falls in on itself, and towards the center of that cloud it gets denser and denser, it gets hotter and hotter, and eventually the particles that the gas and the dust are made of are brought so close together that they start to stick together, they start to fuse. That's the energy source of a star. The star switches on and begins to shine.
Inside every newborn star, hydrogen atoms are fused together to make helium. This process is called fusion, and it creates the energy that powers every star. What happens to a star during the rest of its life depends on how massive it is at its birth.
A star like the Sun is in a delicate balance between gravity, which wants to make the star collapse in on itself, and the pressure that pushes outwards that comes from the energy that's been produced in these fusion reactions happening at its core. However, at some point in the future, the hydrogen runs out, and at that point the core of the star will start to collapse in on itself under its own weight. It gets denser, it gets hotter, until a point where you can actually start to use the helium atoms themselves as the fuel for the fusion, pushing helium atoms together and making carbon and oxygen the next heavier elements in the periodic table.
As the star begins to fuse helium, it creates more energy, and that causes the outer layers of the star to expand. One day, our sun will grow so large it will swallow up the inner planets of the solar system, out as far as the Earth. It will become a red giant. For the sun, this will be the beginning of the end.
What happens is that the outer layers of the star get farther and farther from the middle. The force of gravity that they feel is getting weaker and weaker. And actually, the star loses hold of its outer atmosphere. Its outer atmosphere drifts off out into space. It expands out to become a planetary nebula. And they're some of the most beautiful objects in the universe.
Once the outer layers have drifted away, all that is left of the star is its core.
A white dwarf star is the dead remnant core of a star like the Sun at the end of its life. What's left behind is something that might weigh as much as half the mass of the Sun, but it's only about the size of the Earth. So it's an incredibly dense object, it's dead, there's no nuclear fusion going on anymore, it's incredibly hot, but then over millions of years it will gradually cool down to become a black dwarf.
Some stars, however, are much more massive than the Sun, and they lead very different lives. They are able to fuse heavier and heavier elements inside their core. The star gets bigger and bigger. Some grow up to 1,000 times the size of our Sun, until it has fused elements all the way up to iron.
And once we've formed an iron core, there's no more energy can be got from fusion. That core collapses. The rest of the star starts to collapse in after it, but then it bounces off. There's a huge shock wave, and in just a second, bang, the outer parts of the star are blasted off into space in a huge supernova explosion. These supernova explosions are so powerful that when one of these stars explodes, it can actually outshine the whole galaxy of which it's part, a galaxy of maybe 100,000 million stars.
For these supergiant stars, all that is left is the super-dense core, known as a neutron star, an object that can have a mass greater than our Sun, but be less than 20 kilometers across. But for the most massive stars of all, we think when the core collapses, the gravity is so strong, it becomes a black hole, from which not even light can escape.
So stars are actually the places in the universe where the elements are created.
After the Big Bang, our universe contained only hydrogen and helium. All the other heavier elements were therefore fused inside stars.
The amazing thing is that virtually everything you see around you was made inside a star billions of years ago, before the sun and the planets were formed. And when that star died and blasted its guts out into space, that formed the raw materials from which our sun, the planet Earth, and indeed ourselves were made. And actually, I think that ultimately that's one of the major reasons why I think understanding stars is crucial, because it's actually telling us where we came from.
Okay, so the next thing I want to show you is a double star. And so basically what's happening here is the gravity of these two stars have onto each other, and so they're rotating on themselves, but they're also pulling each other, and they could pull themselves in and eventually collide. And so what's happening here is they're getting faster and they're getting closer, and obviously just like a ballerina or a ice skater, eventually they get so close that they come together and they join. And so pretty cool. I think it's definitely a cool image, and this does happen out there. This has obviously been made up, but this does happen. I also wanted to let you hear what a pulsar sounded like, and basically let's see if this sound. So this would basically be what a pulsar sounds like if you listen to it using a radio telescope. So what you're hearing is every click you hear is rotating like this pulsar. And again, we don't know what it is, and there's all different kinds of them. This one actually is near the center of the Vela supernova remnant. Its rotating period is 89 milliseconds, or about 11 times a second. Yeah, I thought that was pretty cool. This is a made-up image, by the way. So anyhow, well, so that's where we're at, and hopefully you enjoyed it, and we'll if I can figure out how to shut it off again. No. Oh. There we go. I figured it out. Hey, you guys did great. Thanks so much for listening, and I appreciate all you guys do. Have a great day.